So Brian Passwater gives us a pretty fun example here of trying to sketch a graph that has the following information, really trying to get us to understand the conditions that we're about to see for the extreme value theorem. So I strongly encourage you to try this on your own, and then let's walk through it together. So first box here, we have a function that attains a global minimum, but not a global maximum on this interval. So, okay, well, don't just start there. Could start at a minimum. I guess, I mean, doesn't matter where I start. I could have it come to a minimum. And then how am I going to avoid coming to an overall max? Even if I mean, right, at some point, if I get to 5, I don't see a way for me to avoid getting a maximum. This is not possible. Hmm, interesting. We'll kind of discuss where this comes in. All right, we get g of x, we attain an absolute maximum, but not an absolute. That's the same freaking thing. It doesn't change that you put where it is, Brian. It's now over here, but I could say, okay, well, let's start at my maximum and then we'll just go down. But at some point I'm going to have to stop. And it doesn't matter, even if you try to go up again, right? If I'm like, well, maybe it was my problem because I just kept decreasing. But if I do this, well, then I'm going to have a minimum there. So again, not possible. We get into that extreme value theorem. I see it. All right, a function attains a minimum at 2 different values of x, but only one maximum. I don't see why that should be a problem. I can think of that, right? So if I'm doing this one, let's just make like a parabola. We'll have 1 at 1 and 1 at 8, and then we'll go whoop, pretend I actually got to that point at 8. Okay, it has a minimum at 2 different values of x, both at 1 and 8. Same minimum, but it happens twice, and one maximum. Yeah, that's possible. All right, and then we have another interval from 0 to 4. It is continuous, but does not have a max or a min value. So one thing you might try to do here, if you're, being clever about it, is you might sit there and be, I haven't used red because these are not possible. You might be like, well, what if it's a straight horizontal line, Kelly? What about then? Then every value is a max and a min. So that's also a not possible. So this all leads into the whole point of this section, the extreme value theorem, where we have this idea that if we're on some interval a, b, with those closed brackets, then there is both an absolute minimum and an absolute maximum. It doesn't say they are unique, right? It could happen multiple times, like we had in the one that was possible, but we are guaranteed to have both. There's no way to not hit a max or a min value if you're on a closed interval. We have 2 conditions. Those conditions, think about these drawings I had, right? I kept all of my graphs continuous just because that's how my brain works. But that is one of our conditions, right? We need a continuous function and it needs to be on a closed interval. All right. So those are what we would call conditions. If you're filling out these notes, I'm filling them out for you so you have them. This idea that our function must be continuous. That's our condition. Oops, continuous. And our interval must be closed. If this is true, then we are guaranteed that we will have an absolute min, whoa, I can't write, min and max, come on, max exist. That's what happens. Now let's discuss why we need those 2 things. Well, it's easiest to show you a counterexample. So let's think of a situation where we have a non-continuous function. So something like an infinite discontinuity would be one where we don't reach, even if we have a closed interval, that infinite discontinuity, we don't have an absolute max or min because our graph continues off forever towards infinity and negative infinity to either side, right? So this would be a problem. This is why we need our continuous graphs. More than anything else, it's for the infinite discontinuities. Now, why does our interval need to be closed? Well, because if we don't have a closed interval, we might have something that looks like, well, it doesn't even need to be if we just went on, parabola itself. Again, same situation as my infinite discontinuity. If you want something even simpler, I could just do a problem like this, where I have an open circle. Ugh, I got a little bit carried away with that open circle. Maybe I'll do that so it's much more obvious. And we have an open circle at this right endpoint. Our max value, we never really get to it. Because if you tell me that this max value is, say, 5, it's not really 5, it's 4.99999 if we don't actually reach the maximum value. So this is why we need those endpoints to be closed in order for this to actually work. So there's our extreme value theorem. This is in calculus what we call an existence theorem. If certain things are true, we are guaranteed the existence of an absolute max and min. We've had two other theorems like this before. The intermediate value theorem. This told me if we were here at some point and here at some point and our function was continuous, then we must have crossed through any y value between those two in the x values between the two x's that we had. And our mean value theorem. Our mean value theorem had two conditions if we had a smooth and continuous curve or differentiable curve. Then at some point on an interval, the tangent line slope would match the slope of the secant line for that particular interval. So they were giving us, yes, there exists some c on the interval where such and such is true. So extreme value, where we hit our max and min, IVT, where we hit some particular value of y that was in between our two output values, and MVT, where our tangent line slope is the same as our slope of our secant line. So those are our existence theorems. Now we're going to put this all together with the candidates test and how we use this to find that absolute minimum and maximum value on our closed interval for our continuous function.